I want you to picture something for a second. Just imagine looking up at a perfectly clear night sky, way out in the country, away from all the city lights.
Right, where you can actually see the stars.
Exactly. You see thousands of stars, maybe that faint, dusty glow of the Milky Way. And I mean, if you have a decent telescope, you might even spot those little smudges that are distant galaxies.
Oh, yeah. It's a beautiful sight.
It is. But see, if you're like most of us, you were probably taught a very specific way to imagine the actual space between all those objects. We're taught to imagine the universe as this giant stretching rubber band.
Or like a balloon being blown up. That's the classic analogy.
Right, the balloon. Space itself is expanding. And as that rubber band stretches, any photons of light traveling through it, they basically get drawn out along with it.
Yeah, their wavelengths physically stretch out over billions of years.
Which shifts them into the red end of the light spectrum. It's a very clean, honestly very comforting visual. You look up, you see redshifted light from distant galaxies, and you just point to the rubber band and say, well, there it is. Space is stretching.
Yeah, I mean, it really is the bedrock of how we understand our place in the cosmos today.
Yeah.
It's highly visual, it's intuitive, and, well, it neatly explains why almost everything in the universe appears to be rushing away from us.
Because the space between us is growing.
Exactly. When Edwin Hubble and others first observed that light from distant galaxies was shifted toward the red part of the spectrum, the most logical explanation, drawing on Einstein's general relativity, of course, was that the metric of space itself was expanding. The light wasn't just moving through space, the space it was moving through was getting bigger.
But what if that rubber band doesn't actually exist?
That is the big question.
Right, like what if the universe, the actual fabric of space, isn't stretching at all?
Well, that's exactly what we're exploring today. And, I mean, to do it, we're going to have to completely dismantle that whole balloon metaphor from the ground up.
Okay, let's unpack this, because today's deep dive is venturing into some truly uncharted paradigm-shifting territory. The date is Thursday, May 14th, 2026, and our mission today is to explore this radical new paper by George James Dukas.
Yeah, redshift in transdimensional unified field theory.
Or DDUFT for short.
Yeah.
And honestly, reading through these sources, this paper takes literally everything we thought we knew about the cosmos and just completely reimagines it.
It's a heavy lift, mathematically speaking.
Oh, it's dense. But it replaces the whole idea of an empty vacuum of space with this incredibly complex, multidimensional structure called a philatus. And in doing so, it redefines the speed of light, it redefines gravity, and it even offers a completely new mechanical explanation for the Higgs boson.
Which is wild. But we should probably state right up front, we aren't here to declare standard cosmology dead.
Oh, definitely not.
I mean, general relativity and the standard model of particle physics have been spectacularly successful. They predicted black holes, gravitational waves, a whole zoo of subatomic particles. And the author of this paper fully acknowledges all of that.
Right, we're not taking sides here.
Exactly. Our goal today is just to impartially explore this fascinating alternative structural level of physics. We want to understand how this specific theory attempts to explain the cosmos without needing to, mathematically insert invisible placeholders like dark energy or an expanding spatial metric.
So to do that, we have to start with the absolute basics, which means we have to ask you, the listener, to basically unlearn something fundamental.
Learn the vacuum.
Yes, unlearn the concept of the free photon and this deeply ingrained illusion of empty space. Because in the standard model, a photon of light is basically treated as a free, independent entity moving through an empty background.
Yeah, a discrete little packet of energy.
Right. I always picture it like a baseball thrown across a completely empty, frictionless field. It just flies through the void. But TDUFT demands we abandon that image entirely, right?
Completely. What's fascinating here is that TDUFT explicitly rejects the whole concept of empty space. And historically, physics has gone back and forth on this quite a bit.
Like with the ether in the 1800s.
Exactly. Newton believed in an absolute empty void. Then 19th century physicists thought space must be filled with a luminiferous ether to carry light waves. Then Einstein's special relativity came along and showed we didn't really need a mechanical ether to explain light, so the void returned.
Only to be replaced again by quantum mechanics.
Right, the quantum vacuum, which is this boiling sea of virtual particles popping in and out of existence.
Right.
But TDUFT proposes something fundamentally different from all of those.
A philatus.
Yes. The universe is filled with a densely structured, multidimensional operator network, this philatus. In this framework, a photon is not a baseball flying through the air. A photon is simply a node on this lattice.
Okay, so if it's not flying through space, how does light actually move from point A to point B? I was trying to wrap my head around the mechanics of this when reading the sources, and the best analogy I could come up with is a stadium wave.
Oh, that's a great way to look at it.
When you're at a crowded baseball game and the crowd does the wave moves all the way around the stadium, sometimes incredibly fast, but the individual people aren't running around the stands.
Right, they just stay in their seats.
Exactly. They're just standing up and sitting down in a highly coordinated sequence. So in this theory, the people are the nodes, right?
That's exactly the right way to visualize the mechanics of propagation here. Propagation in TDUFT is not translational motion through empty space. A photon doesn't have a tiny little engine pushing it across a void.
It's just energy moving through the crowd.
Precisely. Propagation is a continuous sequence of rephasing events from one node to the next. The energy in the alignment state is passed along the lattice structure. The photon is essentially a localized pattern of excitation, a geometric state that hands off its properties to the adjacent node.
Okay, but I'm struggling a bit with the physical reality of this. If space isn't empty, what exactly is this lattice made of? Because you mentioned the 19th century ether, and this sounds awfully close to that. Didn't the Michelson-Morley experiment and Einstein, didn't they supposedly prove that a physical ether doesn't exist?
Well, they proved that a mechanical ether doesn't exist.
What's the difference?
They proved you don't have a physical substance like a gas or a fluid that exerts, say, wind resistance on the Earth as it moves through it. TDUFT's lattice is not a mechanical fluid. It's an operator lattice.
Operator less.
Yeah, it's a mathematical and geometric framework of interaction. To understand what it's conceptually made of, we have to look at the two foundational rules of this new physics. The paper lays them out very clearly.
Okay, lay 'em on me.
First, geometry is additive. It's represented by what the author calls the dimensional ladder. Think of geometry as fundamental building blocks or structural capacities. You stack them, and they add up to create the space.
Additive geometry. Got it. And the second?
Second, wave structure is multiplicative. It's represented by recursive scaling.
Multiplicative wave structure, like fractals.
Exactly like fractals. A pattern multiplies and scales within itself indefinitely.
Okay, so additive geometry and multiplicative waves. That sounds, honestly, quite abstract. How do those two things actually interact to create a photon of light?
They interact precisely at the nodes. These two systems, the additive geometry and the multiplicative wave structure, they attach at the nodes of the lattice to equal unity.
Unity, meaning the number one.
Yes. Unity mathematically is the number one. In this framework, the number one represents perfect closure. It represents stability and structural balance. When a node is perfectly balanced between its geometry and its wave state, it's at unity.
And what if it's not balanced?
Conversely, separation or a total lack of connection equals zero.
So the photon, as it travels, as that stadium wave moves around, it is essentially riding this incredibly delicate balance between 1 and 0.
Yes, and that balance is an active dynamic process. When the stadium wave reaches a specific node, that node must instantly adjust itself to maintain this balance of unity. This brings us to a crucial concept in the paper, the local rephasing map.
The rephasing map.
Right. As the photon state moves, as the wave passes from node A to node B, the lattice ensures the photon maintains that balance of 1. But here's the catch. The lattice isn't perfectly uniform everywhere.
Right, the crowd in the stadium isn't always the same. Some sections are crowded, some are empty.
Exactly. If the local conditions of the lattice change, the node has to dynamically adjust its internal wave properties to keep that balance. And this is the core thesis of the entire paper. This is the big reveal right off the bat.
The red?
Yes, redshift. That stretching of light we've been observing for a century and blaming on the expanding universe will ultimately be shown to be the result of microscopic adjustments within this operator equation to maintain that balance of unity.
Wow. So it isn't space stretching the light over billions of years.
No, it's the light actively adjusting its own frequency to remain stable as it navigates through a dynamically changing lattice.
Which just completely flips the script on cosmology. If redshift is just the light adapting to the lattice, then we don't need the universe to be expanding to explain what Hubble saw.
We don't. The whole model changes.
But if light is just a stadium wave moving across this lattice, we desperately need to know the rules governing the fans in the stadium. To stick with that analogy, we need to know what controls the nodes and forces them to adjust.
Right, the operators.
Which brings us to the two foundational pillars of reality in this paper. Phi and psi.
These are the two primary operators that dictate absolutely everything in the TDOFT universe.
Yeah.
They are the rule makers. Let's start with phi. Phi is the wave geometry operator.
And just to clarify for everyone listening, we are talking about the actual Greek letter phi, which mathematically represents the golden ratio, right? Roughly 1.618.
That's the one.
I was honestly stunned when I read this part of the source material. The golden ratio is this famous, almost mystical mathematical proportion. We see it in the arrangement of petals on a flower, the spirals of a pine cone.
The shape of nautilus shells.
Yes, and even the sweeping arms of spiral galaxies. And this paper is taking that exact number and using it as the literal baseline for wave recursion in quantum mechanics. It's taking this beautiful, naturally occurring macroscopic geometry and saying, hey, this is the fundamental structural code of light at the smallest possible scale.
It's a profoundly elegant structural claim. The paper argues that nature scales up using the exact same rules it uses at the fundamental level. Phi dictates the velocity structure, the wave stiffness, and the intricate balance of longitudinal and transverse modes of the wave.
Okay, let's break those down. What do we mean by wave stiffness and longitudinal versus transverse modes in this specific context?
Think of phi as the operator that controls the ideal shape and rigidity of the wave pattern. A higher effective phi means the local lattice is stiffer, more structurally sound.
Like a tighter drum skin.
Good analogy. A stiffer lattice yields a higher stabilized frequency for the light passing through it. As for the modes, imagine a slinky.
Okay, I have a slinky in my head.
If you push it forward and back, the wave travels in the same direction you pushed. That's a longitudinal wave, like sound. But if you shake it up and down, the wave travels forward, but the actual motion of the rings is perpendicular.
Like ripples on a pond.
Right. That's a transverse wave. Light has to balance both types of structural energy as it moves through the lattice. And phi is the mathematical ratio, the golden ratio, that dictates exactly how that energy is distributed to maintain perfect stability.
Okay, so phi is the geometry, the stiffness, the ideal structural blueprint of the wave. What about the other pillar, psi?
Psi is the time, alignment, and attenuation operator. If phi is the ideal blueprint, psi is the harsh reality of execution.
Oh, harsh reality. I like that.
It represents the time texture of the lattice, and it dictates the difficulty of alignment at any given point in space. If a particular region of the lattice has high psi, it means there is strong attenuation. It demands more time and more energy for the node to align its geometry and achieve that closure of unity we talked about earlier.
I think I need a physical way to picture this. Imagine you are trying to walk from one end of a swimming pool to the other.
Okay.
Phi is your walking stride. It's the geometric form of your movement, the ideal, perfect mechanics of your hips and knees and ankles working together in a rhythmic cycle. That's your structural blueprint.
Right, the form.
But psi is the physical resistance of the water. The water actively fights your movement, demanding more time and more physical energy from you to complete that exact same geometric step.
That's a great way to visualize it.
If the pool is empty and just filled with air, psi is very low. You can walk easily. If it's filled with water, psi is higher. Your stride takes longer. If the pool is filled with thick, heavy molasses, psi is incredibly high. You are expending massive amounts of energy just to force your leg through the fluid to maintain your walking motion.
And that dynamic is precisely what the photon experiences. And what's crucial to understand here, and the paper heavily emphasizes this mathematically, is that phi and psi do not commute.
Wait, do not commute, like in the sense that 2 times 3 is the same as 3 times 2. That's commutative, right?
Exactly. In standard math, order doesn't matter for multiplication. But in operator mechanics, if two operators don't commute, it means the order of operations fundamentally changes the outcome.
So it's not reversible?
No. It means they interact in incredibly complex, entangled, non-reversible ways. Applying phi then psi is not the same as applying psi then phi. When a node moves or rephases in the lattice, it experiences differential attenuation. To use your pool analogy, the resistance of the water, the psi, actively affects the execution of your stride, the phi. As the photon propagates, it can't just blithely maintain its perfect golden ratio geometry. It has to constantly dynamically negotiate between the ideal wave geometry dictated by phi and the temporal drag, entropy, and alignment difficulty imposed by the local psi.
So the photon is constantly doing this frantic mathematical dance at the speed of light, constantly trying to stay at a balance of 1 while the universe throws different, completely unpredictable levels of phi stiffness and psi resistance at it.
Precisely. The photon is an active participant in its own survival. And this deeply entangled relationship between the lattice's stiffness and its time resistance leads us directly into what might be the most controversial assertion in the entire paper.
Oh, absolutely. Because if phi and psi fundamentally control the medium of the lattice and the lattice exists everywhere in the universe, then the speed of light cannot simply be a static universal number carved in stone.
Right, it changes everything.
The paper explicitly tackles this. It redefines the speed of light. And it doesn't just suggest it conceptually, it gives a highly specific equation for the local speed of light. I want to talk through the mechanics of this equation because it looks intimidating on the page, but the story it tells is actually very intuitive once you break it down.
It is structurally beautiful. It shows that the speed of light isn't just an arbitrary number that the universe pulled out of a hat. It's a built phenomenon. The math for the local speed of light, CLE-local, boils down to a geometric baseline, which is slightly adjusted by the recursive wave structure of phi, and then penalized by a tiny fraction of resistance caused by psi.
Okay, let's walk through those three pieces. First, the baseline.
Right, the math starts with a dimensionless geometric baseline of 2.
Just the number 2.
Just the number 2. It comes from what the author calls the D2 additive backbone, which we'll discuss in depth when we get to the dimensional ladder. But for now, just think of the number 2 as the raw, unvarnished structural foundation of propagation. If there were no waves and no resistance, the propagation factor would just be 2.
Okay, so the foundation is 2. Then the math adds in adjustments based on phi, specifically inverse powers of phi.
Those are the multiplicative wave corrections.
Yeah.
Remember, phi is the wave geometry operator tied to the Golan ratio. Because the wave is fractal and recursive, it adjusts the baseline speed. These mathematical terms, adding the inverse of phi and the inverse square of phi, they are the precise geometric fine-tunings made by the wave structure interacting with the flat dimensional backbone.
So it's shaping it.
Exactly. They shape the raw propagation into an actual stabilized wave.
And then finally we have the penalty. The math subtracts a term called epsilon.
Yes, minus epsilon. Epsilon is a tiny, incredibly small attenuation term. And what drives epsilon, it is driven entirely by psi.
The resistance.
Right. It is the cumulative drag, the entropy, the microscopic alignment resistance of the local lattice. It's the thickness of the molasses in your swimming pool.
Okay, but I have to play devil's advocate here for a second because if you walk into any university physics department today and declare that the speed of light changes, you are going to get laughed out of the room.
Oh, without a doubt.
I mean, Einstein's special relativity, the foundation of modern physics, is built entirely on the postulate that the speed of light in a vacuum, c, is an absolute constant for all observers everywhere. Does this paper just throw Einstein out the window?
No, and if we connect this to the bigger picture, it doesn't throw Einstein out at all.
Yeah.
It provides the microscopic foundation for him. The paper is very careful to clarify this. It states that colloquial is an emergent stabilized propagation scale.
Emergent.
Right. Let's think about what a vacuum actually is in this theory. A vacuum isn't nothingness. It's simply a region of the lattice with extremely low psi, extremely low resistance.
So the pool is just filled with very thin air.
Exactly. In those conditions, the penalty term epsilon is so unfathomably small that the resulting co-local perfectly, flawlessly matches our measured constant c of roughly 300,000 kilometers per second. The paper explicitly states that this does not declare the universal constant c is widely variable in standard operational practice.
So we wouldn't notice it here on Earth.
No. The measurable departures are predicted to be way below current experimental bounds in any typical environment we've ever tested.
So to make sure I'm really grasping this, Einstein wasn't wrong. He measured the speed of light in a vacuum and he found a constant. But what this paper is arguing is that Einstein measured the result of a deeper micromachinery. He measured the macro effect.
Yeah,
It's like measuring the speed of sound in a room at room temperature and declaring it a constant. It is a constant under those specific atmospheric conditions. But TDUFT is offering the atmospheric blueprint. It's showing us the temperature and pressure equations that actually produce that constant.
That is a brilliant way to phrase it. It reveals the underlying operator mechanics that generate Einstein's constant. But, and this is a massive but, it also theoretically leaves the door open.
To what?
Well, if you were to somehow encounter or engineer an environment where psi, that time texture and alignment resistance, was incredibly high, the epsilon penalty term would grow.
Yep.
And if epsilon grows enough, the local stabilized phase speed of that node would microscopically, measurably shift.
Wow.
It completely redefines the speed of light from the magical, fundamental law of the void into a physical emergent property, the lattice's geometry and resistance.
Here's where it gets really interesting, because if we have just redefined how light actually propagates and how its speed is structurally generated by the lattice, we finally have the tools we need to tackle the main title of the paper. We can finally redefine redshift.
Yes, the core phenomenon.
We can abandon the stretching rubber band of the expanding universe. In TDUFT, redshift is not a stretching wave at all. It is purely a change in the relational state between the emitter of the light, the lattice it travels through, and the detector that catches it.
It's all about that balance sheet. The photon node is simply keeping its ledger balanced between 1 and 0 as it moves. The paper provides a single, unified relational equation for this observed redshift.
One equation for everything.
Exactly. And unlike standard cosmology, which requires multiple different physical theories to explain different types of redshift, TDUFT does it all in one elegant sweep.
Before we look at how TDUFT does it, let's just remind everyone how standard cosmology handles redshift today. If you take an astronomy class, you learned that there are 3 distinct types of redshift, caused by 3 totally different physical mechanisms, right?
Correct. First, you have Doppler redshift. This is caused by relative motion. If a star is moving away from you, its light waves are stretched out, just like the siren of an ambulance drops in pitch as it drives away from you.
Right, Doppler effect. And the second?
Second, you have gravitational redshift. This comes from Einstein's general relativity. If light is climbing out of a deep gravity well like a dense star or a black hole, it loses energy, and its wavelength stretches to the red. It's fighting gravity.
Makes sense. And the third?
And third, you have cosmological redshift. This is the big one we started the show with. The galaxy isn't necessarily moving through space away from us, but the space between us and the galaxy is expanding over billions of years, stretching the light in transit.
3 totally different explanations: motion, gravity, and stretching space. But TDUFT absorbs all of them into one relational equation based on phi and psi. Let's explore how. The math essentially says that the observed redshift is the result of a ratio of phi multiplied by an exponential difference in psi, plus something called path attenuation.
It sounds complicated, but it's very logical.
But let's break that down into real-world terms.
Let's use a tangible analogy to understand those 3 lattice conditions that cause redshift. Redshift happens first if the effective phi, the wave geometry stiffness at the detector, is different from the effective phi at the emitter.
Okay, so a difference in stiffness.
Second, it happens if the psi, the time density or alignment resistance at the detector, is higher than at the emitter. And third, it happens due to a path, which is the cumulative path-integrated attenuation as the photon travels over vast distances.
A path. Cumulative attenuation.
Right. Every time the node rephases, every time the stadium wave moves 1 seat over, there is a minuscule chance of mode mixing and energy loss. Over cosmological distances, that A-path term accumulates.
So the analogy I thought of when reading this was international currency exchange.
I like where this is going.
Let's say you start a trip in Europe with exactly 100 euros. That 100 euros is your emission state. It's the pure light leaving the star. But you are traveling to a small town in the United States. By the time you reach the detector, which is the bank in the US, the exchange rates have changed the value. The exchange rate is the phi and psi values. It's the local economic geometry and the local economic resistance of the destination compared to the origin. If the economy in the US is stiffer or slower than Europe, the raw numerical value of your money changes in relation to where you are.
That covers the emitter-detector mismatch perfectly. But what about the journey itself?
Right, the journey is the A path. On top of the final exchange rate, every single intermediate bank or ATM you used along your journey took a tiny, microscopic transaction fee. A fraction of a percent here, a fraction of a percent there. That is the accumulated path attenuation.
The A-path.
Yes. By the time you finally arrive and look at your cash, you only have the equivalent of 90 euros. The intrinsic value of the money didn't magically stretch while you were sitting on the airplane. The actual relational metric of the currency changed between the origin and the destination, plus the accumulated friction of the journey.
That perfectly illustrates the mechanism. And what makes this relational equation so powerful is how effortlessly it replaces the 3 standard cosmology redshifts. Let's look at Doppler redshift, relative motion.
Okay, how does TDUFT explain motion without stretching waves?
In TDUFT, motion doesn't stretch a wave. Instead, relative motion between the emitter and the detector simply creates a local phi mismatch. A moving detector literally experiences a dynamically different projection of the wave geometry operator than a stationary one.
Because it's moving through the lattice.
Exactly.
Mm.
Its local exchange rate is different because it's actively moving through the structural nodes. If you plug that mathematical phi mismatch into the TDUFT equation, it perfectly precisely recovers the classic linear Doppler shift. No wave stretching required.
Okay, so motion just alters your local interaction with a lattice geometry. What about gravitational redshift? Why does light get redder when it climbs away from a massive star?
Gravity, as we will explore in detail in a moment, radically modifies the time density of the lattice. It creates a gradient in psi. If you are deep in a gravity well, near a massive star, your local psi is incredibly high. The molasses is very thick.
Hi.
Right. If the light travels from that high psi environment to Earth, which has a much lower psi, there's a massive differential. If you plug that psi difference into the equation, you perfectly reproduce general relativity's gravitational redshift. It's not light losing energy fighting a gravitational pull, it's light navigating a stark gradient in lattice alignment resistance.
Which just leaves the giant one, cosmological redshift, the stretching universe.
In TDUFT, cosmological redshift is simply the natural, unavoidable evolution of phi and psi over billions of years, combined with the massive accumulated A-path transaction fees from traversing the ether. It is all one single mechanism. The photon constantly negotiating its mathematical survival with a deeply complex lattice.
Okay, but this raises a massive glaring question. We're talking about phi changing and psi changing and these intense gradients in the lattice. What physical structures in the universe are actually causing these shifts?
Yeah, that is the next logical step.
If it's not expanding space tilting the board, what is? Why is the lattice thicker in some places and thinner in others? This brings us to a massive conceptual leap in the paper. The dimensional ladder, a concept called delta D, and how this directly creates the illusion of dark energy.
To understand what physically tilts the lattice and creates these gradients, we have to revisit that additive geometry we mentioned earlier. We have to understand what the lattice is actually built from.
Right, you said it wasn't just a simple grid.
The lattice isn't a flat 3D grid like graph paper. It is built from discrete, stacked dimensional subspaces, which the author categorizes as the dimensional ladder. The paper focuses heavily on 5 primary mathematical indices, D2, D3, D4, D8, and D12.
I found this really hard to visualize. When we say dimensions in everyday life, we mean up, down, left, right, forward, backward, or, we mean parallel universes from a sci-fi movie. But that's not what this paper means by dimensional layers, is it?
No, not at all. Think of them more like layers of a cake, or perhaps better yet, separate channels on an audio mixing board. They exist in the same space, but they govern entirely different physical capacities and operators. They're stacked structural rules. Let's go through the primary ones.
Yeah, right at the bottom.
The baseline is D2. This is the photon plane. It supports fundamental charge degrees of freedom. It is the primary mathematical manifold where photon events, like the emission and absorption of light, actually take place.
Okay, so D2 is the layer where light lives and breathes. What about D3?
D3 is the magnetic and rotational layer. It mediates transverse coupling and angular momentum. When a wave needs to twist or create a magnetic field, it's utilizing the operators on the D3 layer.
Got it. And D4.
Then we have D4. This is the gravitational layer. The profound structural operators that produce what we macroscopically experience as gravity originate entirely on this layer.
And it goes deeper than that, right? D8 and D12.
Yes, these are the deep foundational layers. D8 is the ether support layer. It enables long-range coherence. It's the structural reinforcement that ensures a light wave doesn't just fall apart and dissipate into static after traveling a few feet.
That's the backbone.
Precisely.
Mm-hmm.
And D12 is the deep origin layer. It contains the highest order, most fundamental structural operators that influence the global topology of the entire universe's lattice.
Okay, so we have these stacked layers of rules. D2 for light, D3 for magnetism, D4 for gravity. This leads us to the critical concept of delta D, or the dimensional alternation amplitude. What exactly is delta D?
Delta D is the measure of the local tilt, or the active mixing of these dimensional layers.
Yeah.
In a perfect, completely empty vacuum far from any galaxies, the dimensional occupancy is stable. The layers are perfectly parallel. They don't interfere with each other.
The mixing board channels are totally isolated.
Right. But what happens when you introduce massive objects? Think about standard general relativity. It says a massive object, like a sun, physically bends the rubber sheet of space-time.
Right, the classic visual of the bowling ball sitting on trampoline, warping the fabric so everything rolls toward it.
TDUFT completely discards the trampoline. In this framework, space-time doesn't bend. Instead, a massive object creates a high delta D.
A high-dimensional tilt.
Yes. It causes the dimensional layers, specifically the D4 gravitational layer and the D2 photon layer, to heavily mix, cross over, and mathematically tilt into one another. This dimensional tilt directly and forcefully alters the local time density. And what did we establish time density was?
That's psi, the alignment resistance, the thickness of the molasses.
Exactly. High delta D violently drives up local psi. The layers are mashed together, creating massive structural resistance, and the paper provides a highly specific mapping for this mechanism that perfectly reproduces the macroscopic math of standard general relativity.
Wait, it perfectly reproduces Einstein's gravity math.
It does. It mathematically states that the local gravitational coupling, G local, equals the baseline universal gravity G0 divided by 1 plus delta D squared, all squared. What this profoundly means is that strong gravity isn't curved space at all. Gravity is a localized dimensional tilt that drastically increases the local psi alignment resistance, making it harder for operators to function.
So gravity is essentially just a localized traffic jam in the dimensional ladder. The layers get mixed up, the traffic gets dense, which forces the photon to work incredibly hard to maintain its geometry, which drives up psi, which shifts its frequency to the red to compensate. That is absolutely wild. It replaces a geometric curve with dimensional friction.
It's a completely different mechanical worldview.
But okay, if we zoom out from a single star or a single galaxy, what about the entire universe? What about dark energy? In standard cosmology, astronomers look at distant supernovas. They see their light is redshifted in a nonlinear way, meaning the further away they are, the faster they seem to be accelerating. And physicists say, aha! The expansion of the universe is accelerating. There must be an invisible, undetectable dark energy pushing the fabric of space apart.
This is where TDUFT makes its boldest, most aggressive cosmological claim. In this framework, there is no accelerating metric expansion of space whatsoever, and therefore, there is absolutely zero need for dark energy.
So how does TDUFT explain those supernova observations? Because the data is real. The light is redshifting in a nonlinear curve. If space isn't accelerating outward, what is causing that curve?
It goes directly back to our relational equation and the concept of path attenuation, the A path. Remember the transaction fees on the currency exchange?
Right, the little microscopic losses at every ATM.
Over immense cosmological sightlines, we are talking billions and billions of light years. The lattice itself is evolving globally. The baseline phi and psi of the entire universe are slowly changing as the cosmos ages. Furthermore, the photon is accumulating differential attenuation based on the varying environments it passes through over those billions of years.
So the exchange rate of the universe is constantly shifting while the photon is in flight.
Yes. If the local attenuation density, the sheer amount of psi resistance a photon inherently encounters, was higher in the distant, younger past than it is now, then the accumulated A-path transaction fees will grow superlinearly the further back in time you look.
It compounds.
Exactly. The mathematical result of integrating that dynamically evolving path resistance produces a visual curve on a graph that is identical to the curve standard cosmologists currently attribute to accelerated metric expansion.
So it merely mimics acceleration. It looks exactly like the universe is speeding up, but really the photons from the early universe just had to slog through a much denser, higher psi, thicker lattice to get to us, so they took a dramatically heavier hit to their frequency along the way.
Precisely. It elegantly slices away the need for an invisible, completely undetectable dark energy fluid making up 70% of the universe. It replaces a mysterious cosmological repulsive force with the natural aging, structural evolution, and cumulative resistance of the lattice itself. The observational signature through a telescope is identical, but the underlying physical mechanism is profoundly, fundamentally different.
It's a massive paradigm shift. It feels like taking off a pair of glasses you didn't even know were smudged and suddenly seeing the room clearly.
It really does.
But speaking of paradigm shifts, we have to talk about how these interacting dimensions affect the actual physical nature of matter. Because exploring how these dimensional layers mix leads us to what is arguably the most provocative, mind-bending part of the entire source material. The photon node life cycle, and specifically, the transient mass state.
This section is truly revolutionary because it attempts to conceptually unify light and mass in a way that is highly unconventional. Standard physics treats massless particles like photons and massive particles like electrons or quarks as fundamentally different beasts governed by different fields.
Right. Light is over here, matter is over there.
But the paper outlines a unified 5-stage life cycle for a photon node as it propagates, showing how mass can actually emerge from light.
Let's walk through these 5 stages. Stage 1 is emission.
Yes. Emission occurs primarily at the D2 layer. A source, like a star or a light bulb, provides enough energy to excite a node, specifically on the D2 photon plane, and the wave begins its sequence.
And stage 2 is propagation.
Right. This is the stadium wave we've been discussing. The node passes the excitation along to the next node, constantly undergoing mode rebalancing between its longitudinal and transverse components, constantly negotiating with the stiffness of phi and the resistance of psi.
And then we hit stage 3, which the paper calls the ATT gate. We are going to skip over that for just a second because we have a whole section dedicated to it at the end. Let's look at stage 4 because this is the absolute jaw-dropper. Stage 4 is called the D2 to D3 resonance.
This is where the theory directly tackles the concept of physical mass. During its propagation, as it navigates the varying resistances of the lattice, a photon node may be violently forced to cross the boundary between the D2 photon plane and the D3 magnetic and rotational plane.
Because of that dimensional tilt we talked about.
Yes, the delta D. When the lattice is highly tilted, these layers bleed into each other. When a photon is forced across this dimensional boundary, it experiences what the author defines as a dimensional resonance.
And the paper actually provides a clean equation for this moment of resonance. It states that mass, m, equals the speed of light, c times the gravitational constant, g times the time factor, t, all divided by the dimensional alternation squared, delta d squared. What does that actually mean conceptually?
What this equation implies is astonishing. It means that for a fleeting, almost unimaginably brief moment, the inherently massless photon, which is supposed to just be a pure excitation on the D2 plane, is forced into a highly complex structural configuration that possesses an effective mass state.
It becomes massive.
It becomes massive. It is a transient, inherently unstable condition that is physically required by the lattice to reconcile the massive energy transfer across that dimensional boundary.
Okay, but here is the kicker, the part that made me literally sit up in my chair. The paper calculates the mass of this transient state. It claims that this mathematical dimensional resonance specifically aligns with the 125 giga-electron volt energy range, 125 GeV.
Yes, the numbers match perfectly.
Now, for anyone who follows particle physics or remembers the massive news out of CERN a decade ago, that number should set off massive alarm bells. 125 GeV is the exact observed mass of the Higgs boson, the so-called God particle, the fundamental particle that supposedly gives everything else in the universe its physical mass.
Are we saying, is this paper genuinely saying that the Higgs boson, the cornerstone of the standard model of mass, is actually just a temporary traffic jam of light crossing dimensional boundaries?
That is exactly what the author is proposing, and it's a monumental claim. In the standard model of particle physics, the Higgs field is treated as a distinct, universe-filling energy field. Particles wade through this field and their interaction with it drags on them, which is what we perceive as mass. But in TDUFT, there is no separate, independent Higgs field.
So where does mass come from? Mass emerges strictly as a mechanical necessity to reconcile the wave geometry balance back to 0 and 1. When the violent D2 to D3 crossing creates a massive structural imbalance in the photon's wave state, the lattice produces a massive resonance to absorb that energy and correct the imbalance. That mathematical resonance perfectly matches the 125 GeV Higgs state.
It's like the universe's dimensional machinery has a momentary physical glitch, a temporary failure to process the photon smoothly across the layers, and the resulting literal spark of friction from that glitch is what our colliders measure as the mass of the Higgs boson.
And because it is a transient resonance designed to bleed off excess structural energy, it is inherently fundamentally unstable. It cannot last. It quickly falls away. The photon relaxes back down onto the standard D2 plane, restoring its structural stability and entering stage 5, which is stabilized closure.
Back to being a normal photon.
It's exactly. Yeah. The photon returns to its normal massless propagation, but its frequency has been permanently altered, redshifted, by the sheer energy required to negotiate that massive state. This is a radical, profound unification of physics. It claims that mass is not a fundamental intrinsic property of matter floating in a void, but rather a geometric consequence of light fiercely interacting with the dimensional ladder.
I am still genuinely trying to process the scale of that claim. Mass is just light getting temporarily caught in the dimensional gears of the universe. It's just wild.
Yeah.
But let's move to the final piece of this puzzle. Because the photon has survived its journey, it's navigated the stiffness of phi, it's pushed through the molasses of psi, it's maybe even flashed into a Higgs boson for a nanosecond. But this deep dive isn't over until the photon actually hits a telescope.
Right, the measurement.
Until it is measured. Which brings us to the observer effect and the concept of alignment threshold time, or ATT. This was stage 3 of the life cycle that we skipped over.
And it is perhaps the most philosophically profound concept explored in the entire paper, because it completely redefines our relationship to the universe. In classical physics, and even in standard astronomy today, measurement is viewed as entirely passive. You build a telescope, you point it at the sky, and you simply catch the light that falls into the mirror. The detector doesn't change the light, it just objectively records what is already there.
Right. You're just holding a bucket out in the rain, catching whatever water falls into it.
Exactly. But TDUFT introduces what it calls the resolution principle. It states that quantum measurement is never passive. It is an active, dynamic, physical negotiation. A detector, whether it's a human eye or a billion-dollar digital sensor on a space telescope, is a physical object composed of its own local lattice structures. It has its own local phi stiffness and its own internal psi resistance.
So the detector itself is part of the lattice.
Yes. When a photon node arrives at the detector, it does not instantly magically register as a data point. The incoming node state must mathematically and structurally align with the local lattice conditions of the detector to achieve that final closure of unity.
And crucially, this complex alignment process takes time.
It takes time. This is the alignment threshold time, the ATT. It is strictly defined as the minimal interaction duration required for the local alignment process to successfully produce a stable, closed measurement state. And the key variable here is that ATT scales directly with the local psi.
The resistance of the detector material?
Right. If the detector is situated in a high psi environment, or if the physical material of the detector itself has a high internal resistance, the ATT is longer. The detector physically requires more microscopic time to fully negotiate and process the reality of the photon.
Okay, so different detectors made of different materials or operating in different modes take vastly different amounts of microscopic time to register a hit. Why does that microscopic delay matter for something as grand as cosmological redshift?
Because the incoming photon from a distant galaxy is not a pristine, perfect, uniform wave by the time it reaches Earth. It has been battered, scattered, and attenuated by its billion-year journey through the evolving lattice. It arrives not as a single pure note, but as an ensemble of slightly different phases and mode weights. The wave is messy.
Like a static-filled radio signal.
Exactly. And because of this, the paper outlines a truly mind-bending prediction. Suppose you have two completely different telescopes, detector A and detector B. They are sitting side by side on Earth, looking at the exact same distant quasar. But detector A is a rapid-fire photon counter with a very short ATT. It registers hits instantly. Detector B is a slow integration spectrograph with a much longer ATT. It collects light slowly.
So they're looking at the exact same light, but they have fundamentally different reaction times.
Yes. And because detector A closes its measurement so quickly, it preferentially registers the earliest arriving, most easily resolved subset of the wave state.
Yeah.
The parts of the wave that survive the cosmic journey with the least amount of scattering and attenuation. It samples the cleanest part of the signal.
Okay. And detector B?
Detector B requires more time to achieve closure. It effectively holds the measurement gate open longer, which means it physically integrates the later arriving, more heavily scattered and more deeply attenuated portions of the wave structure into its final reading.
Wait, are you saying?
The rigid mathematics of TDUFT dictate that detector B will record a slightly different stabilized frequency than detector A. Detector B will record a systematic, measurable redshift relative to A purely because it's longer in test. ATT forced it to sample a more heavily attenuated subpopulation of the exact same incoming wave. Two telescopes, same star, same moment in time, entirely different physical redshifts.
That is, wow. That is just incredible. To put that in everyday human terms for everyone listening, imagine two people are listening to the exact same audio recording of someone speaking. But person A has a brain that processes auditory input instantly, while person B has a slight auditory processing delay. It takes their neurological pathways just a fraction of a millisecond longer to fully integrate the acoustic wave.
Okay, I follow you.
What this theory is essentially saying is that person B would literally physically hear a deeper voice. They would hear a lower pitch, a redshifted voice, simply because the physical act of their brain measuring the sound took longer and absorbed more of the scattered low-energy sound waves.
That analogy perfectly captures the gravity of the resolution principle. It is a radical, fundamental departure from standard measurement theory. It implies that the recorded redshift of a distant galaxy is not solely a property of the galaxy, nor is it solely a record of the expanding space it traveled through.
It's entangled.
It is a deeply entangled joint property of the source, the path, and the specific structural alignment dynamics of the specific detector you chose to build. In TDUFT, the active measurement actively creates the final stabilized reality.
Okay, we need to zoom out and synthesize all of this, because we have covered an immense, staggering amount of theoretical ground today. We started with the classic, comforting model of the expanding universe, the stretching rubber band that we've all been taught for a century. We've taken that rubber band and replaced it with a deeply connected, dynamically resonant, multidimensional phalatus.
We threw out the void.
We did. We've learned that light isn't a free baseball flying through an empty vacuum. It's a stadium wave of interconnected nodes constantly, furiously negotiating their geometry, which is dictated by phi and the golden ratio, against the time resistance and entropy of the universe, which is psi.
And through that incredibly complex operator lens, the very concept of redshift is completely redefined. It is no longer an artifact of an expanding metric space pushing galaxies apart. It is a ledger. It is a historical mathematical record of photons' interactions, its mode rebalancing, and its accumulated attenuation as it strives to maintain unity and stability across billions of years and multiple dimensional layers.
We've seen how gravity isn't a curving trampoline, but rather a localized dimensional tilt that creates friction. We've seen how the terrifying mystery of dark energy might just be an illusion caused by the nonlinear evolution of lattice resistance over deep time. And we've seen how even the mighty Higgs boson, the God particle itself, might just be a transient dimensional glitch, a spark of mass in a photon's life cycle. It is a breathtakingly ambitious framework. It attempts to rewrite the rulebook from the ground up. But as we always have to ask on this show, where do we go from here? Math is beautiful, but physics requires proof. What are the next steps?
The author of the paper is incredibly clear-eyed about the open problems and the massive amount of future work required. A theory, no matter how elegant, is only as good as its testable, falsifiable predictions. The paper proposes several highly concrete avenues for experimentation.
Tell me they can actually test this.
They can. First, laboratory tests. We can use advanced polarized laser cavities and plasma tubes here on Earth to intentionally manipulate local phi and psi environments and look for those mode-dependent frequency shifts in a controlled setting, completely eliminating relative motion from the equation.
So testing it on a workbench.
Exactly. Second, deep astronomical surveys. We need to analyze the sightlines of distant quasars. If TDUFT is correct, light passing through dense, high-psi galaxy clusters should show highly specific mode-dependent distortions and line-shape asymmetries that standard metric expansion simply cannot account for mathematically.
Looking for the smudges.
Right. And finally, we need to aggressively test that ATT observable effect we just discussed by pointing multiple high-precision instruments with varying integration times at the same cosmic sources and hunting for those microscopic discrepancies in redshift.
So the ball is entirely in the court of the experimentalists now. They have to go out, build the rigs, and see if the underlying lattice actually behaves the way this gorgeous mathematics predicts.
Exactly. It requires a profound conceptual shift from building massive telescopes that merely act as passive buckets collecting light to building highly sensitive quantum experiments designed to interrogate the physical alignment dynamics of the measurement process itself.
And that leads me to a final provocative thought I want to leave you with today. Something for you to mull over on your commute or while you're making dinner tonight. Think back to that ATT concept we just talked about. The profound idea that our instruments actively negotiate the properties of the light they absorb. If that is true, then we are not merely passive spectators sitting in a dark cosmic theater, just kicking back and watching the universe unfold on a distant screen.
We are participants.
Exactly. The very act of us looking at the stars, the very act of a human being building a telescope and letting a billion-year-old photon strike a digital sensor, forces the universe to reconcile its deepest mathematics. It forces the chaotic probability of the wave to collapse into a stable closure of reality. So are we just measuring a cold, dead cosmos? Or by the sheer magnificent act of observation, are we fundamentally structurally participating in the stabilization of reality every single time we open our eyes? Think about that the next time you look up at the night sky. The rubber band of the expanding universe might be an illusion, but your physical, mathematical connection to the light is far more real and far more vital than we ever dared to imagine.